if you have another system of capacitors connected in some sort of an arrangement, and the whole thing is connected across a supply of 10 volt, and there's a switch S, and the question is, once we close this switch and once the system reaches electrostatic equilibrium, how much of a charge is transferred from the battery into the capacitors? To calculate this, we again have to calculate the equivalent capacitance across the two ends over here, as you can see. So let's begin, and what I'm going to do now is I'm going to start with copying this whole thing. Okay, let's try and investigate this and see whether we can find any two capacitors to be in series or in parallel with each other. Let's begin with 6 and 9. 9 and 6. Look at these two guys. Do you think they are in series with each other? Look at them very carefully. The answer is no, they're not in series with each other, because if you were to take a charge Q, I mean, you know the exercise now, take a charge Q and try to see whether all of that charge can move from one plate of one capacitor to the second plate to another plate of another capacitor. And the answer is no, they're not going to do that, because there's going to be some of the branching off going on over here. And therefore, these two guys are not in series with each other. Okay. What about these two capacitors over here, 6 and 4? Are they in parallel with each other? Well, in order to be in parallel, they have to be connected across the same points so that they end up having the same voltage. Let's check that. So let's say that this point is A, then this point is going to be A. That's nice. What about this one? Let's call this point as B. Then this point is going to be B. But this is not B. This point is not the same as this point. There's a capacitor in between, and surely there's going to be some charge on that once we close the switch, and because of that there will be some potential difference, and so this guy is not at the same voltage as this point, and hence they are not going to be having the same potential difference. So these guys are not in parallel with each other. Bad luck. However, as we do this, I can see two capacitors in series, and the question is, can you see it as well? Well, if you're seeing it and if you say these two capacitors, then very good, because they are in series with each other. Because now if you take this charge Q and you were to dump all the way over there, you would see, yes, all the charges will move from here to here, and therefore these two guys are definitely in series with each other. Okay, and there's a small yellow arrow mark over here, and that arrow mark is just asking us the question. You have to calculate what's the charge on that plate. So you have to calculate the charge on that plate shown. So we're going to do that later. Don't worry about that. Okay. All right. So what's going to be the first step? The first step is going to be solving for these two capacitors in series. So what we need to do is we need to find out what is equivalent of 4 series. I don't know how I'm going to show series. I'm going to just say S. 4 series 12. What's that going to be equal to? And 4 series 12 is very easy. You're going to do 1 over CS is just going to be 1 by 4 plus 1 by 12, and that's going to give us 3 plus 1, and that is just 4 divided by 12. That's 1 over 3, and so the series capacitance of 4 and 12 is just 3 microfarad. So what we'll do now is we'll just erase these two capacitors, and we'll replace them with one single capacitor. Right, so here is one single capacitor, and that capacitance will be 3. Alright, so that is our first step. And now when we go to the second step, we're going to do the same thing. We're going to take this guy, we're going to copy that guy. So let's copy, and now we will see whether we can find any two capacitors in series or parallel. These guys are not in series. This guy is nowhere in the picture. Let's talk about him a little bit later. But what about these two guys now? Are they in series or are they in parallel with each other? They look to be in parallel, but let's make a check. Well, the way we're going to make a check is we're going to assign this point A. Well, this point is going to be A, no doubt about that. What about this one? If I call this as B, notice the same point comes over here because there are no capacitors in between. Oh, these two kind of capacitors are connected across each other, and hence they are going to be in parallel with each other. And therefore we can just use the parallel formula, 6 parallel 3. What is 6? 6 parallel 3. Well, that's easy. That's just 9. And therefore what we're going to do now is we're going to erase these two capacitors. I'm going to replace them with again one single capacitor, and that one single capacitor is going to be 9. Now you may ask, where should I put it? Well, you can put it wherever you want. These 2 points are exactly the same. So I'm just going to get rid of this whole thing over here. Forget about that. And let's put one single capacitor. Alright. Here is going to be our single capacitor, and that's going to be 9. And I think from here onwards, things are pretty straightforward. I mean, I don't know about you, but I think this is pretty straightforward from now onwards. So let's copy this guy again. Okay. Zoom in, and yeah, we're fine with that. And now let's look at these two capacitors. I'm pretty sure you can see them. They are in series with each other, right? You can do that. You can see that all the charge is going to flow from here to here. So 9 series 9 is just 9 by 2. That's going to be 4.5. Right? 9 series 9 is 4.5 for us. So we're now going to replace these two capacitors with a single series capacitor. 9 by 2. Okay, and that is going to be okay, that's going to be 4.5 microfarad. So this is 4.5 microfarad, and I'm pretty sure you can find out, or you can see this, what's going to happen here. These guys are in parallel with each other, so let me just go ahead and draw that instead of copying it again. So I'm going to replace these two guys with just one single capacitor, and that is 4 plus 4.5. So the new, and that's, I think it's going to be my last circuit, is going to be just 4 parallel 4.5 is just 8.5. So this is going to be 8.5 microfarad, and connected across this cell of 10 volt, and this switch over here Alright, okay, so this is where we have, this is our last circuit, and now the question is, once I close this switch, what's going to happen? Well, once you close that switch, charges are going to get transferred from here to here. Charges are going to flow like this, zoop, they're going to flow back this way, and eventually this guy is going to get some voltage, and that voltage is going to be 10 volts. Alright, so eventually this guy will end up with 10 volts. And when that happens, this guy will be positively charged, this guy will be negatively charged. I'm going to use red for charge. So positively charged, negatively charged. And when that happens, charge transfer stops. And so we can now calculate what was the maximum charge that was transferred. I mean, how much charge was transferred from the battery. And the charge transfer from the battery is going to be Q is equal to C into V. And so the charge transferred Q is 10 times 8.5, and that is just 85. And since this is in micro, 85 microcoulomb. Ta-da! There we have it. That's our answer. Our first question answer is total charge transferred by the battery in the electrostatic equilibrium is 85 microcoulomb. But we are not done yet. We're not out of the woods yet, because we still have to calculate charge on this plate. And that's going to require some work, because we need to now start going backwards. Whatever we did earlier, we have to do the same thing. In the last problem, what we did, we're going to do the same thing. Alright, but if you have followed me in the previous problem, you should be able to follow me here as well. So let's do this. Let's go backwards. When I go from here to here, I see that this capacitor 8.5 got split up as parallel capacitor, hence they're going to end up with the same voltage. So this guy is going to have 10 volts, and this guy is going to have 10 volts. 10 volts each. And so we can now calculate what the charge is. Charge is just Q is equal to CV. So 40 microcoulomb here, and 450 microcoulomb over here. That was easy. Now let's go further back. Further back over here. Alright, let's ask ourselves, what do we know? This guy is done, and I don't really care about that guy. Okay, but this is what I care about. This capacitor got split up as two capacitors in series, and therefore they're both going to end up having the same charge. 450 microcoulombs, 450 microcoulombs. and therefore they're going to have this voltage. Now we can easily calculate what that voltage is going to be, right? I mean, this was 10 and these two are same capacitors, so it has to be 5 volts each. But you can just do Q by C. 450 divided by 9, that is 5. Wait, what? I think something went wrong. It's not 450. Oh gosh, I'm sorry. It's not 450. It's 45. So this is 45. This is 45. Alright, so it's supposed to be 45 microcoulomb. Let's rub it. Alright, 45 micro. So yeah, you have 5 volts over here, 5 volts over here, and 5 volts over here. Okay, but we're not done yet. Let's go even further backwards. Let's go here. Okay, notice now, this is the capacitor I'm interested in, which got split up as 2 capacitors in parallel. That means they're going to end up having the same voltage of 5 volts. This guy will have 5 volts and this guy will have 5 volts. I'm interested in this capacitor because that's the one eventually that I'm going for. So this guy will have 5 volts. Oops. So here is 5 volts. Okay, it's going to get messy now. 5 volts, and so 3 times 5 is 15 microcoulombs. So this guy is going to end up with a charge of 15 microcoulombs. Are we done? Are we done? No, almost done. We want this plate, this capacitor, so we'll have to do one last backtracking, and we're going to ask ourselves, how did this capacitor split? It split as 2 capacitors in series, and therefore they're going to end up having the same charge. And then we're going to find out, yeah, we're done, because they're going to have the same charge, 15 microcoulomb. So this one is going to have the same charge as 15 microcoulomb as well. And we are asked on this plate, so I want to know whether that charge is positive or negative. And that's quite easy. You see, charges are going to flow this way, right? So you're going to go like this, and going to split up, and blah, 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 and go out the way. But this has to be positive. And so there's our answer. This plate is going to end up with plus 15 microcoulombs. Alright, so our answer number 2 is that the charge on the plate charge is plus 15. Ta-da! Bingo, done. See you next time.